In this video, we're going to talk about purity formulations and chromatography, and specifically the pure substances. We'll talk about what they are, what examples of them are, and then we'll also go into how you can identify them using melting point and how you can then look at some substances that aren't pure via chemistry but are pure via nature. Now, in chemistry, the pure substance is a single element or a compound. So have your periodic table in front of you. It's all the elements on that periodic table. They are pure, okay? If they're impure, so they're not mixed with anything else. Now, it says not mixed with anything else. That's the important thing. You can also have any compounds that you make in chemistry as long as, again, they're not mixed with anything else. Okay, so one simple activity to do, stop the video and then go along here and just write down some examples of each one of those. Try and remind yourself of some of the examples. Now, if we go through a couple of them, we can't do them all, but we'll give you a couple each. Giant metallic, where we've got sodium, and we've got iron. They're elements on the periodic table. They're not having anything else added to them, so therefore they are pure according to chemistry. Giant covalent, diamond, pure according to chemistry, has nothing else added to it. Silicon, pure according to chemistry, doesn't have anything in it. And you can see here I've just listed some giant metallic materials and some giant covalent materials. Now let's move on to simple molecules and giant ionic. Simple molecules, examples like water, carbon dioxide. You could have methane, you could have ammonia, you could have lots of other hydrocarbons and things like that, but that's just two of them there. And then we've got giant ionic, calcium carbonate, and sodium chloride. And again, any ionic substances, as long as you don't, and the important thing, mix it with any other substance. That's the pure substances according to chemistry. Now, move this to the side and let's have a look at the melting points. Now, pure elements and compounds melt and boil at specific temperatures. And I'll show you that in terms of a graph. So let's think of water. Water melts at 0 and boils at 100. So there's 100 and there's 0. There's our graph. We've got our minutes going across the bottom and our temperature here. So as the line goes up, the temperature is going up and the time is going up as well. And let's have a look at this. So we start off at this temperature. Again, the temperature doesn't matter. And then we raise the temperature up to 0. And we do that just using a Bunsen burner or something like that. We start heating it up. What we notice when we get to 0 is that for a period of time, the temperature doesn't change. Now that's because temperature is related to the kinetic energy of the particles, how fast they move. So basically, as you heat it up, they move faster until they get to their melting point. When they get to their melting point, you're going to break the intermolecular forces before you can go faster. So basically, those intermolecular forces between the water molecules, okay, are being broken over that time period. And so they don't go any quicker, and therefore the temperature doesn't go up over that time period. And you can calculate all the energy to do with this when you do your physics GCSE. However, after all those intermolecular forces related to the melting are broken, not all the intermolecular forces, just the ones due to melting, okay, the temperature continues to rise as we continue heating it until we get to our boiling point. Now our boiling point, again, we're breaking what's remaining of the intermolecular forces, and we're doing it again for a period of time. Once all of those are broken, the molecules can go even quicker, and so the temperature goes up. Now the white one is our pure substance. We're going to draw the impure substance next. Imagine you added salt to water, for example. Now, just to remind you, where the orange is, that is where heat energy is supplied, but you do not raise the temperature because it overcomes those intermolecular forces between the molecules. Okay, let's move that to the side, okay, and look at our impure substance. Now the impure substance is done in green, okay, but where we are breaking the intermolecular forces is still going to be in orange. So we can see here, we've raised the temperature, and then in orange, just like here, the intermolecular forces are being broken between the molecules. Okay, but you notice this is not a nice straight line, this is a up. Okay, so that means the range of over which it melts is higher. Okay, so for example, this might just melt between at 0, maybe between -1 and 1, it melts over that time period. This one might be -3, -4 that it melts at to maybe 4 degrees. So a larger range of melting temperatures might be on this one because of this line going up. But it's still breaking those intermolecular forces. Once we've broken the intermolecular forces, we go up to the boiling point. So the boiling point here, there's a big difference to notice. We've got the same thing, okay, with the intermolecular force is being broken, but on the boiling, if it's impure, it's higher than the original boiling point. And on the melting point is lower than the original melting point. So it's gone down, it is lower. So that's really, really important. So we have a lower melting point, and we have that higher range at which it melts. And we have a higher boiling point, and again, a higher range at which it boils. But we can see it's definitely higher for the impure substance. Okay, remember the green is impure and the white is pure. Now, if that's the case, let's get this out of the way and have a look at an actual example. So remember, our pure substance has a precise melting point, water, melting point is 0, boiling point is precise, that boils at 100 degrees. Okay, and then with our impure, we have lower than expected, okay, and a wider range for our melting point. And we have higher than expected and a wider range for our boiling point. So impure, worth repeating, lower than expected. If you mix two substances or 3 or 4 together, you're going to expect the melting to be lower than expected. So let's look at an example. So these are examples of acids, but don't worry about that. They could be compound A, compound B, it doesn't really matter. Benzoic acid, mandelic acid, both 115. So you think if they mixed them together, they would be 115 because they have the same melting point. But a 50-50 mixture makes the melting point 88 degrees. That melting point is lower than expected, so it fits this impure here. Impure, lower than expected, and it fits that kind of way. Now I want to talk about an example that you will be used to on the streets and you don't even think about probably, which is salt trucks. So we have salt trucks going around the roads in the winter when there's ice, and then they spread the ice spread the salt onto the ground. That then makes the ice on the ground melt. So normally we have a road and it's covered in bits of ice, as you can see right here. Now, if you add the salt to the ice, okay, it will melt because it's a mixture. The salt and the water is a mixture. Okay, it's impure, so it will melt lower than expected. It's expected to melt at 0, but it melts lower than expected, which means you might have the temperature of -1 degrees, but this melts lower than expected. So that means it will have melted by that point and it won't be ice. And so you add those two things together and you get water. And we've just shown that clearly by droplets there, but you get nice big puddles and things like that from the ice melting. So this process here is used in everyday lives to make sure that we don't slip on the roads due to ice. Lastly, we're going to talk about pure substances, but in terms of nature. Remember, with a pure substance in chemistry, it was just has nothing added to it, and it's a compound, a molecule, or an element. Now, in everyday language, normal language, a pure substance just means it has nothing added to it. It's unadulterated. It's come out of somewhere in a natural state. Okay, for example, pure milk. So a cow that will have the milk taken out of it. It'll be milked, and you didn't add anything to that milk, and then that's a pure substance. There's two major ones I can think of right now, and that is wood and milk. Okay, we don't do anything to the wood before it's treated, it would become impure once I've put varnish on it and things like that. But the wood itself has nothing changed in it. It's in its natural state. Okay, so wood itself would be a pure substance in terms of nature, even when you chopped it up into logs. Okay, and then the milk would be a pure substance coming from the cow as long as we didn't add anything to it. Okay, as long as we didn't do anything to it. Okay, and that would be it. Now, it becomes impure as soon as I do this. Okay, I take that wood and I turn it into some form of furniture. It's not pure anymore in terms of nature. It's got varnish on it and things like that. It's not. Okay, and if it's treated in any way, it's not. Same thing with milk. If I then turn that milk or cream into an ice cream, it's not pure anymore. Okay, so that means just that distinction between it's unadulterated, it's not changed in any way from nature, then it's pure in terms of nature. If it's changed in any way, added to, things like that, it becomes impure in terms of nature.